Assalamu alaikum and good morning everyone. This is MD Shakhawat Chowdhury Shovo and my ID is 12108014. Today I am going to present an important topic from digital signal processing, which is Region of Convergence or ROC. The concept of ROC is closely related to Z transformation, and it plays a vital role in analyzing system stability, causality and signal behavior. In this presentation, I will first explain what is ROC, then discuss its importance, and finally explain the rules for determining ROC with several examples. Let's begin by understanding what region of convergence means. When we take the Z transform of discrete time signal, we express it as a mathematical function of complex variable Z. However, this Z transformation does not converge for all values of Z. The region of convergence or ROC is the set of all values of Z for which Z transform converges to a finite value. In simpler terms, ROC tells us where the Z transform is valid. It is important to note that same Z transform expression can represent different signals if their ROCs are different. Therefore, a Z transformation without ROC information is considered incomplete. Now let's discuss why ROC is so important. First of all, ROC helps us uniquely identify a signal. For example, two signals may have the same Z transform expression, but if their ROCs are different, then the signals themselves are different. Secondly, ROC is used to determine the stability of a system. A system is said to be stable if the unit circle, meaning modulus of Z equal 1, lies inside the ROC. Thirdly, ROC also helps us determine the causality of system. From ROC, we can decide whether a signal or system is right-sided, left-sided or two-sided. So ROC is not just a mathematical concept, it has a practical importance in signal processing and system analysis. Here are the main rules that guide us in sketching the ROC. First, the ROC never contains any poles. Poles always lie on the boundary of the ROC, never inside it. Second, depending on the signal type, for right-sided or causal signals, those that are 0 for n less than 0, the ROC is outside the outermost pole and extends to infinity. So it looks like a disk extended outwards. For left-sided or anti-causal signals that are 0 for n greater than some positive values, the ROC is inside the innermost pole, extended towards the origin. For two-sided signals, non-zero in both positive and negative directions, the ROC is an annular ring between the inner and outer circle defined by poles. Finally, for finite duration signals that are 0 outside a finite range of n, the ROC is the entire Z plane, except possibly Z equals 0 or infinity. These rules will become clearer when we look at specific examples. Let's take a classic right-sided signal example. The discrete time signal is x of n equal 1.5 to the power n u of n, where u of n is the unit step function, so the signal is 0 for n less than 0 and grows or decays depending on the value of a. Its Z transformation is x of z equal 1 by 1 minus 1.5 Z inverse 1 with a single pole at z equal 1.5. Since this is a right-sided or causal signal, according to the rules, the ROC is the region outside the pole, that is z greater than 1.5. This includes all points further from the origin than the pole, extended to the infinity. This type of ROC ensures that the system can be physically realizable, which is why most real-world systems are causal. Now let's consider the opposite case, a left-sided signal. The signal is x of n equal minus 0.5 to the power n u of minus n minus 1, which is non-zero only for negative n and 0 for n greater than 0. The z transformation is again x of z equal 1 by 1 minus 0.5 into z inverse 1. Same algebraic expression as before, but now with a pool at z equals 0.5. Because it is left-sided or anti-causal, the ROC is inside the pool, that is z less than 0.5. Notice the same x of z expression represent two completely different signals depending on whether the ROC is z greater than a or z less than a. Although left-sided signals are not common in real-time systems, they are very important in theoretical signal analysis and mathematical modeling. For a two-sided signal, let's take something like x of n equal 0.5 to the power n u of n minus 1.5 to the power n u of minus n minus 1. A typical two-sided signal might have z transform with poles at z equal 0.5 and z equal 1.5. The right-sided part contributes a pole at z equal 0.5 with ROC z greater than 0.5, while the left-sided part contributes a pole at z equal 1.5 with ROC z less than 1.5. So the overall transform to converge, the ROC must be overlap. The region where the both conditions are satisfied, which is the ring where z greater than 0.5 and z less than 1.5. So the ROC is the annulus between two poles. Two-sided signals are generally non-causal, and they are often not stable, depending on whether the unit circle lies inside the ROC or not. These signals are mainly used for analysis purposes. Finally, let's look at finite duration signals. Suppose the signal is non-zero only for a limited range, say n equal minus n1 to n equal n2. Its z transform will be polynomial in z and z inverse 1, with no infinite issues except possibly at z equals 0 or infinity. Because the signal has finite length, the z transform converges everywhere except possibly at z equals 0 if there are positive powers of z, or z equals infinity if there are negative powers of z. So the ROC is the entire z plane, excluding z equals 0 and z equals infinity if necessary. This makes finite duration signals very well behaved in terms of convergence. This brings me to the end of my presentation. In this presentation, I explained what region of convergence is, why it is important, and how to determine ROC for different types of signals. My next teammate Abu Kalam will discuss the properties of Z transformation. Thank you very much for your time and attention. If you have any question regarding this topic, I will be happy to answer them.